Okay, now I'm recording already. Alright, recording. Okay, so today's we are going to learn about thermodynamic processes 9.4. Right? So you give me a thumbs up if you understand. Yeah, give some response later lah. Okay. Okay. So thermodynamic processes. Actually, you learn about these processes before, yeah, during your high school. Okay, but you haven't learned about the specific name. So today you will be introduced all the scientific name for all these thermodynamic processes. You learned this before, yeah? Trust me. Okay, define the following thermodynamic processes. So we have isothermal, isocoric, isobaric, and adiabatic. So all four of these, you must understand each of these process. Okay, and then analyze PV graph. PV graph stands for pressure volume. Pressure volume for all the thermodynamic processes. Okay, so for each of these processes, they have their own PV graph, pressure volume graph. Okay. Process where one or more parameters of a system such as pressure, volume, temperature undergoes changes. So these are thermodynamic processes, yeah, where the pressure, volume, temperature changes. And this can happen due to exchange of heat between system and surrounding. You know, remember the first law of thermodynamics? You learn about this. Delta U equal to Q minus W. This first law of thermodynamics is related to the thermodynamic processes. Okay, so exchange of heat means the Q. Okay, stands for the Q. Mechanical work done on the system or by the system. Remember, work done on the system. Work done on the system means compress the gas. Compress the gas. Work done by the system means work done by the gas. Work done by the gas means expansion. Expansion. Okay, so we learned this before in previous topic, and these two, heat and work done, they causes changes to pressure, volume, and temperature. Okay, both of these factors, heat and work done, they contribute to the change of pressure, volume, and temperature, and also they contribute to the change of PV graph. Okay, so we will look one by one. Okay, don't be afraid. I will teach one by one. Okay, slowly. So all right, first I want to talk, before I touch about thermodynamic processes, I want to touch about the PV graph first. Okay, so what is a PV graph? PV graph is actually a plot of pressure against volume graph. So this PV graph is used to represent a thermodynamic processes. Okay, so as you can see, the PV graph, they have 2 points. You see, first point and second point. First point is the initial state. Second point is the final state. So the point represent the state. Okay, so we have initial state, final state, and then we can see the curve. Yeah, the curve. This curve is actually a process. What process is this curve actually? You will learn about that shortly. Yeah. Okay. This curve is actually a process. Yeah. It's either one of these process. I will review the answer later on. Yeah. One of these process. Okay. So the process can either, go from left to right or right to left. Yeah. Not necessarily must go to the right. Yeah. So yeah, we have positive work done and negative work done. Yeah. I will talk about this later. Work done during the process shown by PV graph can be determined by looking at the area under the curve. So you can see area under the curve, that is actually work done. Work done. Yeah. Area under the PV graph. Work done. What work done? What work done is referred to? This work done lah. Work done of the first law of thermodynamics. The work done over here. The work done. Okay. Work done can have positive work done and negative work done. Remember, when do you use positive work done? Positive work done, that means when the gas expand. Negative work done when the gas is being compressed. Negative work done. Okay, so let's look again the graph. Okay, you see, okay, I think I better write something on the notes. Yeah, I prefer writing, drawing. Okay, so this is a pressure volume graph. So I want to explain a little bit about this PV graph. Let me write something. Oops. Oh, okay. All right. Yeah, that would be nice. So pressure, what's the unit? We always use SI unit, Pascal. What's the volume unit? Meter cube, SI unit. Yeah. So pressure, when going up the y-axis means pressure increase. Pressure increase. So going up the, from, let's say, from 0 up to 100 up to 200. So 100 Pascal, 200 Pascal, yeah, going up. So going up means pressure increase, yeah, going up the graph. And then going to the right, yeah, if the graph going to the right, maybe it's here is 10 meter cube, 20 meter cube, 30 meter cube, 40 meter cube. So going to the right means volume increase. Correct or not, class? Yeah? Give me some response, class. You understand, class? Okay, let's say just now I say PV graph is actually to represent a thermodynamic process. So it has an initial state and final state. The process itself is the curve or the line. So area under the graph is the work done. So let's look at maybe look at this graph again. Let's say I have a process, class. I have a process. Let's say start from here. Okay, maybe over here I start from here. This is the initial state. Going to this, going to here. This is the final state. Going to the final state. Okay, class. So the process is going from initial to final. This is the process. Yeah. The line is a process. Okay. So this line, can you tell me what happened in this process? What happened in this process? Pressure is constant. Can you see that? Pressure is constant. But what happened to the volume, class? What happened to the volume, class? Volume increase from 10 to 40 meter cube. Okay. So this is a volume increase. So this is a what we call expansion lah. Going the process is going to the right. It means expansion. This is expansion. Expansion. Understand, class? Expansion. So remember I told you about area under the graph. What is mean by area under the PV graph? Work done. Work done. Okay. And you also learned that you also learn about this. If expansion is positive work done. If compression means negative work done. Okay. So and this work done is represented by the area under the graph. Area under the graph. So now I want you to tell me, class. I want you to tell me this process of expansion, okay, from initial point to final point. So I want to ask you, what is the work done? What is the work done under the graph? Is it positive work done or negative work done? Positive work done or negative work done? Class? Positive work done or negative work done? Positive work done. That's right, because expansion. Okay. So this work done. So the area under the graph, okay, area of the PV graph is actually the work done, and because the graph going to the right means volume increase. Volume increase. So for volume increase, this is a positive work done. Let me write. So this is a positive work done. Understand? Why positive work done? Because for expansion, is work done by the gas. Work done by the gas or the system. That means you do work, right? The gas do work. The gas do work. The gas got do some work. So it's a positive work done. That's how I remember lah. Excuse me. Okay, class. Very easy, right? Okay, let me ask you again. Let's say, let me ask you again. Let's say, so what is this? Okay, so let me ask you something. Let's say the other way around, class. Let's say the other way around. What about if the process go to the left? What if the process? Let's say this is the initial point and this is the final point. The process go to the left, class. The process go to the left. What process is this, class? Compression or expansion? Compression or expansion? So it's compression lah kan, because initial to final to the left. Okay, so it's compression. So this is compression. So compression means work done positive or negative. For compression, is work done on the gas or work done by the gas? Work done on the gas. Work done on the gas. That means the gas doesn't do any work. The gas doesn't do any work. Someone do the work. So this work done is work done negative. Understand? Okay. This is a work done. Area under the graph is negative work done. Because it's compression. Okay, class? Okay, so compression, negative work done. So be careful with the arrow. If the arrow to the left is negative work done, the arrow to the right is positive work done. It depends on the arrow. It depends on the arrow. Okay, let me ask you another question, class. How should I draw? Maybe this time I put a little bit different. Okay, maybe I put a little bit different. Maybe this time is the pressure is at the top over here, 300, not 300, this one. Maybe this is 600. From this point, this point. Initial point is over here. Drop, yeah. Drop is a curve. So is this compression or expansion, class? Compression or expansion? Compression or expansion? Expansion also. Understand? Expansion also. So the area under the graph is a positive work done. Okay? Work done by the gas. Okay? Okay or not, class? If let's say the graph, let's say the other way around, so final is over here, initial is over here. So how should I draw it? Okay, okay, area under the graph. Let's say initial is at the right hand side, the graph go to the left. This is what? This is compression. So this one can. So this is compression. Okay. Compression work done negative. Okay, class. Okay, very easy lah. Area under the graph. Go to the right means positive work done. Go to the left means negative work done. Compression, negative work done. Expansion, positive work done. Okay, class. Another thing. Maybe sometimes the graph is like this. Maybe let me tell. Okay, I need to change. Let's say this time the process is like this. Throw away all these throw away all this. Let's say this time the work done is from here. No, maybe I put it over here. Initial class going to 600 pressure. Let's say 600 pressure Pascal. Going to the same volume. The same volume class. Final is over here. Huh? Class? See? Tell me. I need you to think, class. Think is better. Okay, so there's no area. I tell you the answer already. Okay, class. So let's say the process now is going from below here, going up to a higher pressure. This process. What is the work done? It maintained at the same volume. What is the work done, class? Tell me. Work done is no area, isn't it, class? I don't want to wait for you lah. Yeah. My time is so precious. Okay, so the area of PV graph is actually the work done is 0. No work done. Understand? This is 0 work done, no work done at all. So that means this one no expansion or no compression. Okay, everyone understand, class? Just a thumbs up enough lah for me. Yeah? Just a thumbs up. A pitiful thumbs up, I say. Yeah, pity me. Yeah. So no expansion, no compression. So it's 0 work done. The process also can go down. Also, not necessarily have to go up. It can go down. What's the difference? Maybe some of you will ask. What's the difference between go up and go down or go up? Yeah. The difference is from high pressure go to low pressure. Yeah. Just now is from low pressure go to high pressure. Okay, class. Right now I only introduce you to pressure and volume, right? But if you look at the notes, thermodynamic process is actually the parameters are pressure and volume, right? So right now we just talk about pressure and volume. But there is another parameters, temperature. So where can we look at temperature for this PV graph? Where is the temperature, class? Where is the temperature? You only have pressure and volume. Where is the temperature? So for that, okay, so for that, I will introduce you the temperature parameter, how to look at temperature. So you see it's lagging. I don't like. Someone donate me an iPad lah. Yeah. Okay. Wait a second. Let me have a. Okay. So let me. Okay. I want to write something. Okay. So this hardware. Oops. Okay. So I want to draw again the pressure and volume. PV graph. Okay, understand, class? So P pressure, volume. Where's the temperature, class? Where's the temperature? So just now, as I said, going up is pressure increase, going to the right is volume increase. Now, how about temperature? Temperature is going this way. Understand, class? Going excuse me. Going excuse me. So you see, health is wealth. You know that. If no health, you cannot do things. Yeah. Okay. So temperature. Temperature is going diagonally. That means if pressure is I can say 100 or 200 like that, 300, 600, Pascal. Okay, volume means like 10, 20, up to 80 meter cube. Temperature means we have isothermal line. We have isothermal line. Okay or not, class? That means going away from the pressure volume axis is temperature increase. Is temperature increase. That means this is what we call isotherm line. Isotherm line. What is mean by isotherm line? What is actually, okay, class? Maybe you don't understand what is mean isothermal, isocoric, isobaric. Actually, the word itself tells you the meaning already. What is mean by isotherm? Iso means same. Therm means temperature, thermal. Same temperature. Yeah? Okay, let me write it down. Isotherm line. Isotherm means what? Same what? Same temperature lah. Same temperature. That means along this line, they all share the same temperature. Understand, class? Let's say I have a point over here, point over here, point over here, point over here, point over here. They all have the same temperature, class. Let's say, okay, the isotherm line which is nearer to the axis is lowest temperature, class. Lowest temperature. The isotherm line very far away, from kingdom far away, is high temperature. That means my sound is broken. That what it means. Yeah. So along this line, they all have the same temperature, 300 Kelvin. Make sure you use SI unit Kelvin, not degrees Celsius. So all the point over here, they all is 300 Kelvin. Same temperature. Understand or not, class? They all same temperature, 300 Kelvin. So going further up, maybe this is 400 Kelvin. Going up, this is 500 Kelvin. Along this isotherm line, these are called isotherm line. This maybe is 600 Kelvin. 300 Kelvin is how many degrees Celsius, class? Minus 273. It is actually 27 degrees Celsius. Understand? 300 Kelvin is 227 degrees Celsius. So okay, class. So if any process going further away from pressure volume axis, means they are getting hotter. Getting 300, 400, 500, 600, getting hotter, heated up. Pressure, temperature increase. Okay, let's look back. Let's look back to our process, class. How about go back to our process? You know why I teach this way? Reasons. I have reasons due to experience lah. Okay, so about this first process. I don't want to talk about what kind of process is this first, but I just want you to understand the graph. That's very important. Understand the graph first. Okay, this process going to the right. Yeah, initial point is here, final point is here. That means what happened? Pressure constant, right? Pressure is okay. You can say one thing. You can say what? First, you can say pressure is constant. Correct or not, class? What happened to the volume? Volume increases. Understand, class? Okay okay, not. Boleh lah. Okay, how about temperature? It's not shown over here. Where is the temperature? Yeah, where is the temperature? You draw lah. You try and sketch the isotherm line. How is it fit? Maybe here is one isotherm line, another one. See that, class? The isotherm line nearer to the axis is lowest temperature. I can't believe today I can teach this well. I thought I'm so in a bad situation already, but I think that I teach quite alright. Okay, alright. So this is 300 Kelvin. Yeah, maybe lah. I just simply put a value 300 Kelvin. And then the following line can be 400 Kelvin. And then this line is 500 Kelvin. Okay, class. Tell me, this horizontal line to the right, what happened to the temperature? Tell me. What happened to the temperature? It moved from 300 Kelvin go to the 500 Kelvin. So what happened to the temperature, class? This process? Yeah? Every line, every straight line, every curve is a process. So this temperature, what happened? What happened to the temperature? Increase or decrease? Increase or decrease? Increases. That's right. Yeah. Temperature increases. Good. Give a thumbs up to yourself. Yeah. Okay. How about the process? This one. This process. How about this process, class? So by now it's the other way around. So you should understand already, right? Kan? There's a line, isotherm line. You know, it go from, you know, okay, 300 Kelvin, 400 Kelvin, 500 Kelvin. This one is what? What happened to the pressure? Okay, let's talk about pressure first. Let's talk about pressure. Constant. This one pressure is constant. What happened to volume? Plus, what happened to volume? Compression decreases. Negative work done. Okay or not, class? Negative work done. How about the temperature? Tell me the temperature. Temperature decreases lah, isn't it? Okay. You know, class, actually this is what law is this? A pressure constant. That means it's pressure law. No. This is Charles' law. Do you know that, class? This is Charles' law. Do you know that? Without realize, now you realize that this is Charles' law. Do you learn about Charles' law? Prince Charles. Do you know who is Prince Charles? No, it's nothing related to Prince Charles. It's Charles' law. Pressure constant. Charles' law. Remember what you learned in your high school? You learn about this. V1 over T1 equal to V2 over T2. Understand, class? So this is a Charles' law process. You see, when you heat up the gas, yeah, initially at low temperature. See, low temperature and low volume. Initial at low temperature. Somebody. Okay. Initial at low temperature, low volume, and then you heat up the gas. You heat up the gas. So that means the temperature increase, isn't it? Temperature increase. But what happened to the volume? Volume also increase. Volume is proportional to temperature. Remember that? Remember our formula PV equal to nRT? PV equal to nRT. So when temperature increase, volume increase. Correct or not, class? So we heat up the gas. The volume increase. Volume increase from 10 to 40. And temperature also increase from 300 to 500. But if we make the pressure constant, we make the pressure be constant. All these are constant. This is Charles' law okay. So so that means if you heat up the temperature, heat up the gas, the temperature increase, volume must increase. It cannot decrease. Volume must increase. It cannot go the other way around, decrease. Likewise, if you you know this one, if you temperature decrease, volume also decrease. PV equal to nRT. Remember that? PV equal to nRT. When temperature decrease, volume decrease, pressure constant. Like that. Okay, how about this one? How about this one? Maybe this one on the same isotherm line. Like this one, class. Maybe this one. Why I purposely draw this curve? Maybe all this line over here, all this curve, maybe they fall on the same temperature. They fall on the same temperature. Maybe the initial point and final point at the same temperature. That means maybe both of them are at 400 Kelvin. Below is 300 Kelvin, above is 500 Kelvin. That means from initial point to final point here, they maintain at the same temperature. Same temperature. So what happened to the pressure, class? What happened to the volume? You know, what happened? What happened, class? Let me write something. So this one is temperature constant. Temperature is constant. See that? Temperature is constant because you maintain at the same isotherm line. How about the what happened to the volume, class? This one is going volume going this way, right? Not going this way, so volume decrease. Correct not? Compression. So volume decrease. What happened to the pressure, class? Pressure increase. Boys, this is Boyle's law. Remember? Boyle's law. P1 V1 equal to P2 V2. So that means if you have high pressure, small volume. If you have a low pressure, high volume, like that. Yeah. Or just look at the PV equal to nRT graph. Yeah. PV equal to nRT equation. Yeah. PV equal to nRT. So that means let's say if temperature is constant. Let's say this is constant. Let's say this is constant. So that means rearrange the formula. P equal to nRT over V. See that, class? Volume decrease, pressure increase. This one is constant. See? They are inversely proportional. You see that? Volume decrease, pressure increase. Pressure must increase. You cannot. The graph cannot be like that one. Cannot. Impossible. There's no such graph. The graph cannot go this way. The process cannot go down. Become smaller pressure. No. Because if you decrease, think logically. You decrease the volume of gas, you increase the pressure of gas. Correct or not? Because when you decrease the volume of gas, all the air molecules have to occupy a smaller volume. Smaller volume means higher pressure lah. Understand? This is Boyle's law. You learned before. Okay, I only talk about graph this time. I haven't touched the thermodynamic process. How about this one, class? This one is volume constant. Volume constant. This one is volume is constant. What happened to the pressure, class? Pressure decrease. Pressure. This one go down. That means pressure go down. Pressure decrease. Correct or not, class? Pressure decrease. What happened to temperature? Pressure decreases. Pressure decreases. What happened to the temperature, class? Temperature? Draw lah your graph. Draw your graph. Draw. Excuse me. Draw your graph. So, which one higher temperature? Sorry, construction happening just beside my house. You see that? Very disturbing. Yeah. So, okay. Which one has higher temperature? Initial or final? Which one? You just catch yourself and you find out yourself. Of course, initial one has higher temperature. Yeah, maybe this one is 500 Kelvin. This one is 400 Kelvin. Right, nearer and nearer to the axis, become lower temperature. So final has the lower temperature. Initial has a higher temperature. So that means this process going down is cooling down. Cooling down, pressure decrease also. Make sense of what you learn. Temperature decrease. Temperature decrease. So what law is this, class? This is Gay-Lussac law or pressure law. When volume constant. Remember what the equation you learn? You learn Charles law, kan? Charles law, V1, T1. You learn PV, Boyle's law. Now is the Gay-Lussac law or pressure law. So this is P1 over T1 equal to P2 over T2, class. That means when you lower down the, lower down the temperature, you lower down the temperature, the pressure also get lower. Higher temperature means higher pressure. Make sense, class? Make sense? Enjoy. Enjoy or not? So higher temperature, higher pressure. This one, but volume constant. Higher temperature, higher pressure. Okay, understand, class? Can get it? Okay, only Ryan is one person. How about the others? Are you listening? Or you are reading for your UPS? UPS 3, is it? Okay, I hope you are listening, yeah. Don't pile up your work, until finally, tomorrow I'm going to continue with part 3, part 3. If you don't understand part 2, I'm going to understand part 3. I teach step by step. If you skip a step, that means you don't understand the following step. That's why I pay attention. When I ask to watch, you watch immediately. Okay? Tomorrow I'm going to teach part. Actually, class, tomorrow is physics day, right? Or F4, right? F14, so tomorrow I'm going to finish the whole syllabus. I'm going to finish the thermodynamics until we solve the problem solving. All question. We're going to finish record our video tomorrow. Tomorrow is our last already to cover all our syllabus. Do you know that? Okay. All right. So I hope that you are paying attention, when I'm teaching part 2. Okay, class. So we have covered the basics. What is mean by all this PV graph? By now you get a rough picture already. Now I want to go one by one for the process. Maybe right now I only managed to do 2, or maybe only 1. It's okay, no problem. Actually, I teach everything. I teach all except the adiabatic. Except the adiabatic. Okay, so I need another session. Okay, so isobaric. What is isobaric, class? Isobaric means pressure constant. Isocoric means what? Volume constant. We teach about that. I taught already, right? Isothermal, temperature constant. I talked about the graph already. Adiabatic haven't. No heat transfer is involved. Okay, so I think I only manage for now is 145. I think I teach these 2 lah, isobaric, isocoric. Class, okay? Are you still okay? Still with me? Yeah. So what is mean by actually I feel not motivated to teach today, but somehow I got the energy because I found that I can teach not bad for today. Okay, isobaric. Okay, class, isobaric. As the word itself tells you, what is mean by isobaric? Isobaric. Bar, if you Google it, bar is a unit for pressure. Ada tak? Got right? Barometer. Remember the barometer? Barometer is a instrument to measure the pressure. Barometer. Okay? So pressure, bar is pressure. Iso means what? Iso means what? Same pressure. Yeah? Same pressure. Okay. Somebody worry about we are going online or what? Yeah. I want to finish the syllabus. Everything is online. Yeah, everything is online. Once we finish our syllabus, I record all the video already. we go back face to face. That's it, class. Don't have to worry. Don't have to worry. Yeah. What you have to worry is UPS 3 tomorrow. Okay. Isobaric, constant pressure. So that means this is same pressure. That means I can write it as pressure must be constant. If pressure constant means apa yang berubah? Only volume changes. I've thought about this just now. This is what we call Charles' law. Charles' law. Remember that? Pressure is constant, so Charles' law. So isobaric process is Charles' law. So how the graph look like, class? How the graph look like? Let's just copy paste. Where is our isobaric? Yeah, all these, class. All these. I don't have to, I don't have to just copy it, yeah, and just paste it here. Yep. That's Charles' law, isobaric process. Charles' law, pressure constant. Okay, class. The graph can either, either expansion or compression. Got two situations. Can either expansion or compression. Okay. Fine, everyone. Okay, good, Okay. How about the first law of thermodynamics, class? We need to include the formula for, the first law of thermodynamics. First law. Okay, let me write it down. First law. Okay. First law of thermodynamics. Okay, class. First law of thermodynamics, class. Delta U equal to Q minus W. Okay. So, okay. Now, look at this one, this formula. When do we have delta U, class? When do we have delta U? This is internal energy. Internal energy relate to what, class? Internal energy of gas is the total kinetic energy of gas. Correct or not, class? Total kinetic energy of gas. How do we find the total kinetic energy of gas? 1 over 2 F N K T. So that means the internal energy is related to temperature. It's related to temperature. Okay, so I want to ask you, is there any changes of temperature in this process, isobaric? Is there any changes of temperature? Got changes of temperature or not? Got changes of temperature? Yes, you see, got temperature increase, isn't it? Got temperature increase. So that means temperature increase, that means got delta T, got change of temperature. Got change of temperature means got change of internal energy. Got change of temperature means got change of internal energy between initial and final point. Got change of internal energy. So delta U is not zero. Delta U is not zero. Heat go in or heat absorb or heat loss. This one surely got work done. Got work done, class? Got work done? Got work done? Got. You see, got area under the graph. Right or not? What's the work done? Let's find out what's the work done. For this, the work done is equal to just take the pressure. Pressure is constant, right or not? Multiply by the change of volume. It's like a rectangle shape. Rectangle area. Okay? The pressure multiplied by change of volume. This is the delta V. Understand? Change of volume. And this is the pressure constant. Take the pressure, multiply change of volume. You get the work done. Yeah? Or you can write it as pressure equal to V final minus V initial to get the work done. Understand? V final 40 minus V initial 10. That's the work done. Okay? So And the first law of thermodynamics, the process everything you have over here. Okay, delta U equal to Q minus W. Got. Okay, good. Now last one. Yeah, I know it's 1 for 51. I want to go to our last one, which is isocoric. Yeah, isobaric just now is pressure constant. What is isocoric? What is constant? Volume constant. Actually, isocoric got two names. Yeah, got two names. Let me write it down. Yeah, isocoric. This is isobaric process. Isocoric. 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 It is the same as isovolumetric process. Isocoric has another name. We call it isovolumetric. So as the word suggests, isovolumetric or isocoric. Isovolumetric means what, class? Tell me. IQ question. What is isovolumetric? What is constant? What is constant, class? Tell me. Pity this person who will cough.
Volume.
Teach you, huh? Volume, that's right. Yeah, volume is constant. That's right. So iso means same volume. I don't know coric stand for what. Maybe you can search it out. But I know isovolumetric is the same as isocoric. Isovolumetric means same volume lah. As the word suggests. Okay, so what is constant? Volume is constant, class. Volume is constant, class. So when volume constant, that means what can change? Only the pressure and temperature can change. Only the pressure and temperature can change. This is what we call what law? Pressure law. Pressure law, or infamous name, Gay. Don't say lah. Other people name. Please respect. Gay-Lussac law. Understand? Understand? So this is Gay-Lussac law, pressure law. Okay? Understand? Pressure law. So have we learned the graph for this one? Yes, why not? We have learned it just now. Yeah, indirectly. This one, understand, class? This one. How do I copy it out? Make it smaller. Easy for me to take it out. This other strategy. See that? Okay, so let me put it over here. Time. See that? We have learned it. Isocoric process. This is isocoric process. The graph can go down or can go up. If go down means cooling down. Go down means cooling down. Yeah, from 500 to 300. If the graph go up means heating up. Heating up means pressure also increase. If you cooling down, pressure also decrease. Understand, class? That's it lah. Yeah, this is a pressure law. Now look at the first law of thermodynamics. Just now, first law of thermodynamics. Okay, copy this. Copy that. Yeah. First law of thermodynamics. Let's talk about first law of thermodynamics for this one. Okay, is there any change of temperature? Okay, if you want to talk about change of internal energy, means you must have change of temperature, right? Got any change of temperature, class? Yeah, remember we talked about internal energy, delta U. You want delta U to be positive, has a value. That means you must have change of temperature. Either temperature increase or temperature decrease. Temperature decrease means delta U negative lah. If temperature increase means delta U positive. Okay, this one. Back to the first law of thermodynamics. Okay, go back to this one. So, is there any changes of temperature in this isocoric process, class? Tell me.
Yes.
Yes, that's right. Got change of temperature. They don't maintain at the same isotherm line. They go to the other isotherm line. Like this one, it dropped from 500 Kelvin. Isotherm line go to 300 Kelvin. Isotherm line. That means it dropped temperature. Got change of temperature. So delta U is not positive. Delta U has a certain value. Like this one, like this case, class. Like this case, This case, this case, this case. This one is delta T is negative, isn't it? That means that delta U must be negative also. My secret, yeah, some secret lah. Internal energy decrease, delta U negative. So got value. Delta U is not is not zero. How about heat flow, class? Heat flow, of course, got lah, because you heat up the gas, you know, pressure law. Either you heat up the gas or cooling down the gas. So got heat flow, heat absorb or heat loss. Work done. Class, got work done? Work done? Is there any work done? Is there any work done, class? 3 minutes more. Is there any work done?
No.
No area. So this one, for what process is this? Isocoric process, isovolumetric process. Same volume. Means what? No expansion. No expansion or compression. Means excuse me. Delta V is zero. Delta change of volume is zero. It means work done is zero, class. No area. So that means work done zero. Just work done is zero because no area of PV. Very easy, class. No work done. Okay, class. So this formula is simple lah. Delta U equal to Q only, class. Delta equal to Q only. For isobaric, a little bit more complicated because got delta U, got Q, got W. All three got, all three got. Delta U, Q, and W, all three got. But for isocoric, isovolumetric, no W, zero. So only delta U and Q. Okay, class, that's it. So see you tomorrow, class. Yeah. So tomorrow morning, I will record the part 3, class. Record the part 3, Record the part 3, and afternoon record part 4. And actually, if I manage to finish all the part 3, the afternoon I can record the problem solving video already. Finish everything syllabus. That's how exciting is it, right? So, and at night is our UPS 3. Make sure tonight you prepare for it. Okay? Do your objective questions given. Okay, so see you tomorrow. Yeah, see you tomorrow. Bye.
Yeah, thank you, sir.
Okay.
Thank you, sir.
Yeah. Thank you also.